Is your model predicting the past?
All right, everyone, I hope you can hear me. I'm excited to wrap up this session on demography with a nod to metaphysics. And I'm going to ask if your model is predicting the past. Okay, this is pretty much unfinished joint work with Michael Kim, and I'll tell you where we're at in our thought process. So, you know, I think really core to many debates about prediction and, you know, machine learning and what it does is sort of this fundamental question of when are we justified to use statistics or statistical risk scores in deciding about individuals, and when are we entitled to intervene in individual life trajectories on the basis of some statistical factors. And if you listen to the proponents of prediction, they'll often come up with the following argument that, well, a risk score gives us a look into the future of an individual life trajectory, and if we know that it's going to rain, why would we pack an umbrella, right? So this is an example from a famous paper on this topic. If we know that somebody's going to commit a crime tomorrow, why shouldn't we keep them in jail? That's the example they give. But opponents say, well, wait a minute, that's not the right analogy. Prediction actually punishes individuals for circumstances outside their control, and individuals are sort of given a statistical disadvantage for the environment they came up in. Okay, so these are kind of the two opposing camps. And in this work, we're trying to sort of shed light on this distinction between individual and environment and see if we can illuminate it a little bit further. Okay, so what I'm going to do is to focus on this distinction between individual and environment and argue why it's fundamental to prediction and our debates about prediction. And so I'll tell you a little bit about how you might go about defining it and how you can evaluate it empirically. Okay, and then I'll tell you what it says about the limitations of risk scoring in the social world. Okay, so this distinction between individual and environment, by the way, is absolutely fundamental also to the theory of equality of opportunity. And I'm very fond of the work of John Rimmer, who, in a nutshell, sort of suggested that we should, generally equalize rewards based on individual effort relative to the individual's type. So that's a sort of general allocation rule. And for Rimmer, a type is grouping individuals of similar circumstances. Okay, so he defines circumstances as those aspects of one's environment, including perhaps one's biological characteristics, which are beyond one's control. And he actually worked on this definition of type and environment over the decades, and he kept refining it and changing it in the way he wrote about it, just to give you a sense of how subtle it is to sort of define what environment is. Okay, so this distinction, of course, is a little bit subtle, and if you think about how sort of social outcomes and individual outcomes are determined by our social environment, it's even a little bit, you could say that philosophically, it's not even clear what the distinction is. Okay, and it's certainly challenged by sort of social constructionism and other viewpoints. But since I'm a pragmatic computer scientist, I'm going to skip over this and just sort of say we're going to lean on the crutch of time for this talk. We're just going to make this about time. And we're going to say that there are certain background features in a prediction problem, which are what comes before the individual's agency in time. Okay, the things that are outside the individual's control just by virtue of coming too early in time. Okay, and so the causal diagram that you can keep in mind for this talk is that I'm generally going to partition the features into two kinds. One I'll call W, it's what I call background features. And the other is I call X. Those are the individual features. Okay, and so you can think of this sort of there being in the course of time on the x-axis here, and the W features are all the ones that came before your birth. Okay, so this is just for illustration. So W, X, and Y. This is the simple setup I'm going to entertain, and they both feed into some kind of outcome. Okay, that we're trying to predict from these features, and W influences X. And X has some direct influence on Y as well. Okay, and W possibly also has a direct influence on Y. That's a simple causal diagram. Okay, good. So the main definition we're going to work with of a background predictor is the following. We're going to say the function of X, a predictor, is a backward predictor if it's conditionally independent of the outcome given the background. Okay, so if your prediction is independent of the outcome given the background, what this means is that once you know the background, once you know someone's environment, the scores don't tell you anything. The scores just look random. Okay? They look random to you once you know the environment. I'm going to give you an example in a moment. But I'll note just on formal grounds, if you do the math, obviously the optimal backward predictor for the squared loss if you do regression is just the conditional expectation of the outcome given the background, as you would expect. And for 0-1 loss or classification, it is just the threshold of the conditional expectation. So if it's greater than a half, then you say 1, otherwise you say 0. So this applies both to regression problems and prediction problems, and we can be talking about both. So this is just the optimal solution, what an optimal backward predictor looks like. To give you a real-world example, I'll actually cite another paper that was involved in this. Is work by Juanqui Perdomo, Talani Britton, and Rediat Abebe from just this year. And we studied, the case of high school dropout prediction in the state of Wisconsin, where the Department of Instruction tried to predict, a dropout in student in the high school population across the state, and mitigate sort of dropout by predicting this outcome. And so we wanted to know if these risk scores, the use of these risk scores had really contributed to decrease in dropout across the high schools. Okay, and so what we found is actually that to the extent that dropout is predictable, it's largely predicted from the environment of the student, specifically the school district or the school that the student goes to. And this meant we could argue that there exists an allocation mechanism, a very simple one, just based on the student's school district, that is as efficient, as effective as allocating based on predictive risk scores. I think the microphone is fading, but I'll just keep talking over it. Basically, this got us to think about what does it mean? Do we actually need, or what is going on when the allocation here is basically by environment and not by individual characteristics? Okay, and so the picture I have in mind when I think about backward prediction or background prediction is this. There's basically environments, and each environment has a number. That's sort of the base rate of the outcome, the expected outcome given the environment. But within that environment, there might be many individual sort of units that you learn nothing about. Okay, so there's the 0.5 school, and there's the 0.7 school, and there's the 0.1 school. And you might be going to one of these schools, but I don't know anything about you other than that you go to the 0.5 school. Okay, in particular, from the perspective of the teacher, who presumably knows which school she goes to, once you enter the doors and you're inside the school, the risk score doesn't tell you anything. Okay, you've already learned everything you were going to learn, and looking in addition, to the risk scores is not going to tell you anything more about the students. So your classroom looks like a random labeling of the students according to this risk score. Okay, and so this is also why backward prediction says a whole lot about intervention or the effectiveness of interventions in this context. So do the following thought experiment, which is also from this paper. Suppose now the background or the environment defines a unit like a school, and make two assumptions about these units. The first assumption is that a unit like a school has an intervention at its disposal that has some fixed cost, and it has a fixed effect, some fixed treatment effect and some fixed cost. Okay, and let's say the unit, the school in this case, can target the intervention at least as well as randomly applying it within the budget. Okay, so schools are sort of minimally competent, at least, in that they can allocate at least as well as random. Okay, so their allocation of the intervention that they have is at least as good as random. Okay, and no worse. Then it follows, if you prove this, that targeting the intervention based on the score of a backward predictor within each unit cannot lead to any improvement. Okay, so because the score is random conditional environment and the school allocates at least as well as random, so by sort of using this risk score, you're gaining nothing over what the school is already doing. You can't. Okay, there's just not enough information in the predictor to improve the allocation of the school. This follows from these two minimal assumptions. Okay, so it's very important to know if you're talking about intervention and treatment effects. It's very important to know if you have a backward predictor or not. Okay, because if you do, it puts very strong sort of limitations on its use as a means of intervention. Okay, so how can we measure the strength of backward prediction? How do we go about finding out whether we have a backward predictor in practice or not? Okay, so there are simple sort of common sense solutions here that we'll basically start from. But then there's some subtleties. Okay, so the first idea is to train a predictor based only on the background features and see how well it's doing. Okay, so you just restrict your data to the background features, train a predictor, and see what happens. This is reasonable, but it's actually not the only thing. There's something else that makes a whole lot of sense. You could take the risk score and you can train a model based on the background features to predict the risk. So you're not predicting the outcomes from the background variables, but you're predicting the sort of risk scores themselves. So you're trying to like match the predictions using the background features. That also makes sense. And the nice thing about it is this does not need even access to the target variable. Okay, it doesn't need any outcomes. So in particular, it allows you to sort of audit without having any outcome data. Okay, so you're just trying to understand if a specific predictor used in some kind of setting is a background predictor, you don't actually need outcome labels for that. Okay, so you can do that kind of audit process without any outcome data. Okay, and so here are all the things you could sort of do if you think about it. Okay, so let me put down some more recall and notation. There's the features X, background variables W, outcome Y, and prediction Y hat. One of the standard thing, of course, is to train on XY pairs and evaluate on Y. That's just a standard machine learning pipeline. So I use the notation XYY for that to train on XY and evaluate on Y. But you could also train on the background features and the outcomes and evaluate on the outcomes. Or you could train on the background variables and the predictions as labels and evaluate on the outcomes. Or you could do these two things. You could train on pairs of background features and outcomes, evaluate on the predictions, or you could train on background features and predictions and evaluate on predictions. So these are some sort of 4 possible things you could do with Python if you just invoke various combinations of fit and predict. Okay, so basically the notation is just like which sequence of fit and predict you do in your IPython notebook. Okay, so I'm a simple man. Okay, so fit and predict is how you remember this. Okay, so WYY is just fit and predict, fit WY and predict Y and so on. Okay, so fine. But fortunately, it simplifies quite a bit. So assuming that your predictions are weakly calibrated under some notion of recalibration, it only matters what you evaluate on. Okay, so it only matters what the third lever is, namely which variable you evaluate on. Okay, so WYY is actually equal to WY hat Y. So fitting on Y hat doesn't matter. You're still gonna, as long as you evaluate on Y. And similarly, WYY hat is equal to WY hat Y hat. Again, it only matters what the third letter is. Okay, so really only fundamentally 2 backward basics. You either evaluate on the true labels or the true outcomes, or you evaluate on the predictions. These are the only 2 things. Okay, the others kind of collapse, and it gets even more simpler for regression. For regression, you just have that there's essentially only one because you have this equality that XYY is just WYY minus WYY. Okay, so it simplifies to just one thing. I apologize for the, mic flukes here. Okay, so let's go to the empirical evaluation now that we sort of got the ways of doing this sorted out. And what we did is we looked into various longitudinal panel surveys that are available online, specifically the medical expenditure survey and the survey of income and program participation. These are large-scale panel surveys. So they run over different waves or time horizons. And why do we choose these panel surveys? One of the reasons is that there's a very precise description of the temporality of the features. So you really know that the outcomes in the future, which is often not true if you think about it for like various machine learning data sets that you might use. It's actually not so true like the outcome is actually something that was labeled in the past or that was something that has already occurred as opposed to something that's in the future. So here it's like pretty clear what was in the future, what was in the past, and so on. So there's no sort of confusion about that. So let's look at the MAPS, the Medical Expenditure Survey. This is a survey of households, individuals, and healthcare providers. And it's sort of aimed at providing insights into healthcare utilization across the United States. And we take background variables to be all demographic variables. So anything that speaks to demographic information about the individual. And as a target variable, we find a threshold of total healthcare utilization in a year. So it's a binary prediction problem. Whether you have high healthcare utilization or low healthcare utilization. Okay, and so here's the upshot of what happens when you evaluate these things, and we have simple code available. We're doing this now. So you basically have on each of these rows, you have one classifier. You can look at whichever way you want. Random forest, gradient boosting, logistic regression, 3 standard things. And then actually, it's very crucial that you see this here. Okay. So each column is a setting of features. So there's age is one demographic variable, race is one of them, age and race is one combined, and then you have all demographic features. And look, for example, in the gradient boosting row, you can see that the red bar, which is what happens when you fit y, when you fit on W y and you evaluate y, you get almost the same error. You get almost the same 0-1 loss as just x, y, y. Okay, so W, y, y is just a little bit larger than x, y, y, meaning you can almost predict as well from the background variables as you can from all the variables. There's a little bit of a gain to like individual features in healthcare utilization, but it's surprisingly small and actually speaks to what scholars of like social epidemiology have observed, that like health outcomes are socially determined to a large extent. And this is one way of seeing that quantitatively, that you can really predict almost as well as from all features with just demographic information. If we just know your demographics, I can pretty well predict your healthcare utilization almost as good as with all the features. And we see the same thing on SIP, which is this other survey, panel survey that I'm not going to go into, but we see the same thing. And again, the picture is also kind of the same in this Wisconsin dropout prediction problem that I mentioned. So surprisingly, many prediction problems have this property that you can predict surprisingly well just from demographic information, which should give you pause. Okay? Go on, there we go. So let me wrap up by saying why this is sort of significant and what we should take away. Okay? So this distinction between individual and environment, I argue, is sort of salient for context or evaluation of prediction. And there are many reasons actually for this, and one of the first of them is, I think, normative, because sort of interventions based on backward predictors, they allocate based on features that are outside of our control. They're allocated based on our environments and not based on what we've done. So you could, say that this is maybe not more than one as specific allocation problems. Second, there's a practical problem or sort of a policy problem here, namely that, as I showed to you the simple fact, interventions based on backward predictors are no better than random once you take environment into account. Okay, so once you already look at schools, there's no sort of additional value that you get out of using a risk score that's really a backward predictor. Okay. There's also a rhetorical implication, which is that you should be really, reluctant to call backward predictors individualized risk scores. So when somebody tells you a story about individual risk scores or individual risk, and predicting individual life trajectories, you should really ask, is that actually true, or is that really just a little bit of a story we tell about these predictors? Okay. There's also sociological significance in the sense that backward prediction speaks to the social constitution of various outcomes. And it's kind of interesting that we have this simple, sort of practical approach if we're going about it. Just see how well you can do from these background features. And that gives you sort of a quantitative measure of how socially determined various outcomes are that we're interested in. And so our recommendation is that you should evaluate these backward baselines in any risk scoring application. There's simple ways of doing that. You don't even need outcome labels for it. You can just, all you need are the risk scores and the demographics, and you can do it. It's a very simple test, and it tells you an awful lot about prediction and risk scores in general. So I hope people will start doing this. Thank you.